Hello, everyone. Come on in. All right. Looks like we got about 13 of you already, 14 now. Anybody have any questions while we're waiting for anybody else to show up?
When is the final again?
Your class meets on Tuesday and Thursday, so it'll be Tuesday of next week, a week from today.
Thanks.
And remember, you can start it. This class starts at 11. I'm allowing you to start it as early as 10 a.m. So because you're allowed 2 hours and 15 minutes. So if you started an hour early, then you'll get out the same time you normally do. But if you start it right on time, then you'll need to stay an hour late. But don't start any later than right on time, because otherwise you won't be allowed to do the whole 2 hours and 15 minutes. If any of y'all have a problem with that, make sure you let me know. Like today is pretty much the last chance for you to tell me if you need to take it at the testing center, or if you got some kind of conflict with, another final. The rule used to be if you had 3 finals on one day, we'd allow you to move one and you could choose which one you wanted to move. But nowadays, I'm being a little more lenient. So just let me know if y'all need to do something like that. It will be using Respondus. So I did make the Respondus midterm open again, so you guys can make sure your Respondus is up to date. You might need to, in fact, re-download it because there's a new version or something. I did make all those tests available. You see now we have 2 tests left and a final, but I'm dropping 2 instead of 1, just to keep the stress off of you. But I really want you to take both of those tests, because, if you get better than even your lowest one, then you've done something better. So there's a practice final up there as well. So you got 2 practice tests and a practice final exam, all of which you can use to practice. And to be honest with you, these last 2 tests, taking those are really going to help you on the final anyways. I'm going to blow through today chapters 37 and 38, and then 39 we'll do next time. 39 is, like I said, this is a chapter that you probably already know somewhat about if you've ever had a chemistry course, and they talked about quantum mechanics a little bit. It's, the N, P's, and the S's, and the D orbitals and stuff like that. The N being the principal quantum number, and then the next one is the shell number and all that good stuff. So that's mostly what that's about. But this one's the early quantum, and then actually applying quantum mechanics. I'm relying heavily on the examples in the book because the examples are really super simple. I write them. I've written down several of them just so you can see them, but I'll just explain to you the results because they're so straightforward. They're just literally applying a formula, right? So it's supposed to be, kindergarten or physics work. So anyone have any questions before we get started?
I just have one more question about grading.
Go for it.
So 37 through 39, we're expecting to go through. So those homeworks will be like normally graded, but chapter 41 will be extra credit.
Yeah, 41 is definitely extra credit.
Okay.
And by the way, I've got a lot of the derivations and other problems solved on my YouTube channel already. So if you don't understand, for instance, and you want to understand how to apply Schrodinger's equation for an infinite well or for a finite well and that kind of stuff, I've got those shown on my YouTube channel. And those are sort of the highest level that you're really expected to do in this course, is be able to do that, but I'm not going to test you on that. So I would love you to do those physics problems just like they do in your textbook, and know those results. But I'm not expecting you to be able to derive them. They might actually ask you a question, what's the third energy level for an infinite well or something like that, and then you just have that on your equation sheets. So that'll be fine. That'll make more sense when I get to it, though. Anybody else have any questions? Yeah, 37, 38, and 39 will be on the final, but like I said, I'm streamlining it to sort of a minimum aspect. In fact, there's a quantum mechanics quiz that I made at one time that just sort of shows what I think is most important. I think I'll open that up, and it's not going to be a required grade, but I'll probably make it an extra credit grade. And y'all can do that if you're worried about what's going to be on 37 and 38 and 39. And it gives you more practice, of course.
Yeah, I'd appreciate that.
Yeah, it's already made, so I can do it. Let me do it right now, in fact, so I don't forget. It's not like I ever forget anything ever. All right, here I'm going through my modules in my course, and I'm going down to the practice tests. And it's going to be called Quantum Mechanics Quiz. Let's see if it's actually working. I just published it. It's called Quantum Mechanics Quiz. Make sure it's weird. Like sometimes you copy a test and everything works, and then you get over here, none of the questions are there. Okay, and allow multiple attempts. Any number of attempts is allowed. You can see that answer, yes. And I'm going to say this is available until December. Your test is on the 14th, so I'll say December 13th. All right, so it's open now. It's just quantum mechanics quiz. I currently have it listed as a practice test, but I'm going to take it out of that group because otherwise it'll count as a 0 if you didn't do it, and that will bring your practice test average down. So remember, your practice test counts as extra credit, and what I do is I give you a 0 on any of them that you didn't take, and then I average the highest scores on all the ones you did take with the zeros, of course, and then I move that decimal 2 places to the right, and that's basically how many are 1 place to the right, and then divide it by 2, and that's how you get the number of points I add to your grade. All right, any more questions?
Oh, I have one question.
Oh, I see a chapter 20 question. I'll fix that too. Go ahead, Daniel.
I'm looking at the Zoom page. I noticed that that there are Zoom meetings listed for the 14th and the 16th. Are we having any class on the 16th after the
No, I just did it automatically to cover the whole semester. Okay. So I put in the last day of classes, and it just filled that in automatically. So no, we're not meeting anymore after Thursday. Anything else? I'm working on that chapter 20 thing. I might even make it extra credit. I'm not sure, but I'm definitely going to push it back till it's being due on the 12th or 13th or something like that. But I got it open here, so we'll check that. All right. So what I want to talk to you about is I told you the story before, probably told it to you several times, but in the late 1800s, early 1900s, everybody, if you had polled all the scientists that were really knew what the crap they were doing, everyone would have probably said, there's a few little things about fluid mechanics that, is really complex. I don't think we can ever solve that really. But pretty much the laws of physics are worked out. We're just going to be doing experiments to see that they're right to say 4 or 5, 6 decimal places as opposed to just 2 or 3 or 4 decimal places. But then again, we had this big revolution. The first revolution came up in 1900 when a guy by the name of Max Planck was trying to solve what was called the ultraviolet catastrophe. So we knew, for instance, that light being a wave can come from electromagnetic, or is actually electromagnetic radiation, and that can come from charged particles vibrating. In other words, anytime a charged particle accelerates in any way, that creates radiation. So when you actually heat up let's say a iron poker in a fireplace or something like that, it turns red hot, right? Well, if you took that light and you sent it, say, through a little slit so you could get just a narrow picture, and then you spread that with a prism, say, or bounce it off of a CD or a DVD, you'd get sort of like a rainbow that would roll out on it. That rainbow has a very specific equation representing how much of the intensity of the light came from this wavelength, how much came from this wavelength. So if you made an actual graph of intensity of the light, which is really the brightness, is also the square of the amplitude of the wave, which remembers the electric field and the magnetic field. So that intensity, if you plot that versus wavelength or versus frequency, when you do it versus wavelength, you'll get a very steep curve on the left-hand side. It'll peak and then it gradually falls down. That's what the experimental results told us. Rayleigh had derived a formula for it, and then Jeans sort of did some correction to it. So we called it the Rayleigh-Jeans formula. And that worked pretty well, but it sort of went to infinity in the ultraviolet section of the spectrum. And hence they named it the ultraviolet catastrophe. Wien had come up with another formula, and the formula made an equation that looked sort of like the curve, but it was just off. It was just not good. In other words, it didn't match the data. It matched the shape, but not really that well either. Like it didn't have a steeper side. It was more symmetric and stuff like that. So Planck went to try to solve this problem. And in so doing, he did this little trick that we know from in the past, which is this mathematical trick where you can take a continuous variable like x and treat it as a discrete variable. So now x can only be, say, 1, 2, 3, 4, 5, and nothing in between the 1 and the 2, or the 2, or between the 2 and the 3, and all those. And it could go up infinitely large. That's still fine. It just isn't continuous. It's got little gaps in between things. And when you do that kind of approximation, you can come back and take a limit using the idea of calculus, take a limit to reestablish the continuity of the variable. Okay. Well, he was doing that and he was getting promising results, but then every time that he did that limiting process, it turned out to be crap. So he said, well, screw it. I don't know why, but here, if I assume that the energy of these little oscillating atoms or whatever in a metal gives off energy h times f, or 2h times f, or 3h times f, but nothing in between, and that goes on again for infinity, then I can get a really nice expression and it works well. And that's called the quantum hypothesis. But like your book says, no big deal was made of it at that time. Planck didn't think anything of it. In fact, he just kept working to try to find a easier way to get it without having that non-continuity of a variable. So what we got was this neat little graph, which I've already taken the time to draw out here. So this green line, this red line, and this blue solid line are all graphs for experimental data, if you will, for the actual metal that's being heated up, or the object that's being heated up. And what you see is as you get to smaller and smaller wavelengths, you get a steep peak. But when you get to longer wavelengths, you get a long gradual peak. But there is, a long gradual curve, but there is a peak on it. Okay. And what you also can notice is that the lower the temperature, the farther to the right the peak is. So all these peaks, this is 6,000 Kelvin is what this curve represents, and its peak is over here. The 4,500 is a little to the right of that, and the 3,000 is a little to the right of that. And that is an actual example of part of Wien's law that did, and it's actually pronounced Wien as in with a V like voice or Victor. Okay, even though it's a W, that's just the nature of German language. But anyways, Wien had made up this dot dash dot dash dot dash type of curve that doesn't quite match well enough. Here's the Rayleigh-Jeans curve that's just dash dash dash. And in fact, this equation that Max Planck was able to derive, which is given right here, that was made by making this assumption that the energy of the individual bits of radiation that would come off of the oscillators had to be 1 times h times the frequency, or 2 times h times the frequency, or 3 times h times any number, any whole number of h times f's. But in so doing, he got this equation, which perfectly matched the data. So the solid lines are both experimental data as well as Planck's data, or Planck's hypothesis. Okay. Again, they didn't make that big of a deal about it. And in fact, he was able to curve fit to get what the constant value h was. And he was quite a bit off. We've now determined it pretty accurately to 6.626 times 10 to the negative 34th joule seconds. And that's called Planck's constant. Okay. It's called Planck's constant, named after Max Planck. Okay. Now that was in 1900, and pretty much nothing was done with it. In fact, Max Planck kept trying to find a way to get rid of that stupid hypothesis, and never really did. He eventually grasped and accepted quantum mechanics, but unlike Einstein, but it was still always a problem with him. So one thing that Wien's law did make correct, and that was, what is the relationship of the peak of the curve to the wavelength? So if you took the Wien's equation that he had and you find the maxima on it, then you could actually get this thing that we now call Wien's law. So this is called Wien's law. Again, I'm pronouncing that with a V because that's the way it's supposed to sound. But it basically says the wavelength at which these peaks occur is not the highest wavelength. As you can tell, the wavelength goes way beyond that. It's just the wavelength at which the peak occurs is 2.90 times 10 to the negative third meters times Kelvin over the temperature of the body in the units of kelvins. Okay, so I did an example really quickly. The surface of the sun's temperature is 5,778 Kelvin. At what wavelength does its intensity graph peak? And what color is that? So basically just applying that equation, you can see I plugged in that number and the 5778, and I got basically 502 nanometers. And if you look up 502 nanometers, that's in the green part of the spectrum. So our sun is really more of a green star. Our eyes just are not very good at seeing green. And in fact, you can find neat little essays on how our eyes are not well suited to seeing green, but there's a buttload of green stars in the universe. We just can't tell them. Okay. So that's just a neat little problem, easy peasy, that sort of thing. Another thing you might want to do is say the visible spectrum runs from about 350 to 700 nanometers. That's really what we can see. And a lot of books just say 400 to 700. I've even seen some say 350 to 750 because we're teaching younger and younger people, and it turns out their eyes don't suck like ours. So they can see even further. But generally speaking, the short wavelength side is the blue side and the long wavelength side is the red side. And to remember that, I use well, a mnemonic that might not mean that much unless you know a little bit about the Doppler effect, and that is blue to you. And what that means is if you imagine the waves coming from an object, as that object walks towards you, the waves are going to crumple up and get shorter in front of you, in between you and the person coming towards you, and they're going to stretch out behind you. So since the wavelength's getting shorter, you recognize blue as the short end of the wavelength of the visible spectrum. Okay. So I ask you, what color would this star appear if it had a temperature of 50,000 Kelvin? And that's like Sirius, the star Sirius, not the actor or the character that was played by the actor in Harry Potter. But that star is on the order of 35 to 50,000 Kelvin, if I remember correctly. And they look in the night sky, you'll recognize my answer, but yeah, they look a very different way. But what I want you to understand is, let's use Wien's law to figure out what color that star should be, i.e., where is its peak, right? Now, there's a little trick to that, because if the peak is outside of the visible spectrum, then all that matters is the brightest part of this curve that's in the visible spectrum. So if the peak's over here and the visible spectrum's over here, the brightest part will be on the right side of the visible spectrum, which is the long wavelength. If the peak's on this side, though, the highest part of the spectrum that's in the visible spectrum will be on the left end, which is, of course, the short wavelength end. So let's calculate that and make use of it. So when I did that calculation, you can see I just did 2.9 times 10 to the negative third meters times Kelvin over 50,000 Kelvin. And I got 58 times 10 to the negative ninth meters, or 58 nanometers. Well, we can only see 350. That's the smallest wavelength we can see with our eyes. So that's not in the visible spectrum. And from the graph, you can automatically see, oh, well, that's on this side of the visible spectrum. Because clearly these other colors, the red one and stuff like that and the green one, they were in the visible spectrum. So basically what you're picturing here is, now we're talking about a peak being to the left of the visible spectrum. Therefore, the left end, the low wavelength end of the visible spectrum, is what shows. So we'd say that star is blue, and you will see it as a little bit of a hue of blue, but it also looks sort of white because we're really outside of the visible spectrum. So it looks a little ultraviolet-y. Does that make sense? So that's another simple example. And you can see how simple these examples are in this early quantum stuff. But let's go on. So that was the first big step into quantum mechanics, and it required something absurd. The idea that the energy only comes out in discrete amounts. When you realize the h is so small, 10 to the negative 34th joule seconds, you realize that we probably would never notice that, because you'd have to be at 0.33 zeros and then a 6 before you ever see it. We don't measure anything to that level of accuracy, or precision, I should say. So nothing initially came from that. But in 1905, that impressive year for Einstein, that was the year he introduced special relativity, which could have won him the Nobel Prize. He wrote a little later that E equals mc squared. That explained how the sun worked. He solved the Brownian motion problem, which basically definitively proved the existence of atoms. All that stuff was done in that same year. It's really a remarkable year for him. But he also did this 1905 paper, which was more or less the true creation of quantum mechanics. Planck beat him with the quantum hypothesis, but didn't really attach that to anything, and no one else really did anything with it until Einstein came along and said, I think I can solve the photoelectric effect problem with it. Now, here's a picture of the photoelectric effect, and you guys just had this lab. That's the whole reason I made sure you did that lab. But what you can have is, imagine a circuit where you can adjust the voltage. That's what this little knob is showing right here, is me adjusting that voltage. And I'll put the positive side over here and the negative side over here. And I'm going to take a flashlight. See my cool flashlight? I could beat somebody in the head with it. Be a cool weapon, right? Anyways, so with that flashlight, you can see the photons are hitting the metal. And it turns out that when this happened, they knew it, and it's called the photoelectric effect. They knew that when you shine light on the metal, electrons escape from the metal. They just pop off, and in fact can create a current through a circuit this way, right? And then you could adjust that voltage, and you could get those electrons sucked over here by having a high positive voltage here. That means the electrons want to go there really, really fast, right? But you can also adjust it until only the fastest of electrons can get there. And then you can even adjust it so not even they get there. So you go to the lowest voltage it requires backwards to make them stop. And you say, oh, well, that's the stopping potential. And of course, that's voltage times the electron charge. And that will actually be basically the kinetic energy of the particle at that particular time. So obviously you had enough voltage where you were able to stop it. So you basically converted all the potential energy back to zero by putting a potential on it that was equal in magnitude, but opposite in direction. Okay. So that was what the photoelectric effect was. And it could be understood with the wave nature of light, but there were some problems. The wave nature of light would say, since the intensity of the light is the square of the electric field and the magnetic field, which is always smaller, so it's really just the electric field. If you made the light brighter, then that would mean the electric field was stronger, and you'd expect even more electrons to break loose and go faster. But that was not observed. And well, there was some other issues too, like there's supposed to be a delay. So if you use really low brightness, you could just shine the light on it long enough, and some of those things would start vibrating in the same frequency as the monochromatic light was shining on it. But eventually it'll get enough energy where it can break loose. So there would be this delay if the light was really dim, but it would ultimately come. Well, that's not the way it behaves. And in fact, Einstein said he imagined there was a certain amount of work required to overcome the strength of the pull that the individual atoms have on the individual electrons. And the ones with the weakest hold on them would come off and have the maximum kinetic energy, because the least part of their energy was used to get it out of the actual thing. And he called that the work function. And what he did, he said, hey, if I use Planck's hypothesis that this is going to create little particles whose energy are h times f, then the light is going to be shooting these little particles of energy h times f, and that energy is going to go into dislodging the electron, which is the work function, and it's on the order of a couple electron volts, and it's also a property of the material. So that's another way you can use a particular branch of science to determine whether this metal is gallium or gold or silver or whatever. But it would also, any energy left over would go into the kinetic energy of the electrons. And of course, that would lead to a linear graph. So if you solve for the max kinetic energy, which I already told you how to get by adjusting this voltage, you just do it for each frequency. And what you'll see is there's a cutoff frequency at which if you do any lower frequency, no matter how long you wait, it's never, ever, ever, ever going to get the photoelectric effect. And if the light is brighter, you don't get any effect either. So that was two things that really differentiated it from the wave nature of light. It showed us the particle nature of light. And lo and behold, I think Millikan ended up doing this experiment and got exactly the line that Einstein predicted. He got the slope was the Planck's constant, and he got this breakoff point was the work function of the material divided by Planck's constant. And lo and behold, we had a full-blown quantum mechanics at this point. Someone had used a result that Planck had to say, yes, evidently particles behave as light, or light behaves as particles. Even though we've got all that confirmatory evidence that light behaves as a wave, like the Young's double slit experiment and all that stuff, we now have definitive proof that it acts like a particle as well. So another question you might want to figure out is, well, how much energy do these photons have for a given frequency? So I asked you the question, how much energy does a red photon have? And I let you know that red is roughly 650 nanometers. Again, you can see what happens here. In this case, I gave you nanometers instead of frequency. So I noted, hey, E equals HF, but C, the speed of light, is equal to the frequency times the wavelength of light too. So you can combine those two and get E equals HC over lambda. And that's a different expression than the one we were using before, but it means the same thing. So you see this is 305.8 times 10 to the negative 21st joules. If I divide that by 1.602 times 10 to the negative 19th, then I'll actually get the number of electron volts. And it turns out that a red photon has about 1.91 electron volts of energy. Okay. Now you can use this joule figure, for instance, if you wanted to calculate how many photons in the visible spectrum come out of a light bulb. Your book actually does that. A 100-watt light bulb is not uncommon for only about 3% of that energy to go into actually visible light. That's sort of the problem, and that's why so many people are switching to LEDs and compact fluorescent lights and stuff like that, because they're a lot more efficient. Basically, you're using the fact that wires heat up when current goes through it to make light, but you've got to go to such a high temperature before you ever get there. You're wasting 97% of the energy. So if you take and say 100 watts, multiply that by 0.03, you'll get the amount of energy in the visible spectrum. And now if you divide that by, say, let's say the middle of the visible spectrum, which we would say was 350 to 700, so maybe 500 nanometers. If you did this equation for that, divided the energy that you got from 500 nanometers into the into the 3 watts, then you'd see it takes on the order about 10 to the 18th, 10 to the 19th photons per second. So that's pretty cool. The photons are actually bombarding and shooting out in the visible spectrum, shooting out of the light bulb. And they, have roughly, if they were red, they would have roughly 1.909 electron volts of energy in it. But that tells you, again, how many photons must be coming out. Later, and in fact, now we'll talk a little bit about the momentum of the photon. So you can think, well, if a photon has energy, does it have momentum? And that seems obviously, yeah, because momentum is mass times velocity, and kinetic energy is 1/2 mv squared, which you can also write as p squared over 2m, by the way. But that's classically. And the photon, as I've been telling you in relativity, travels at the speed of light. And in fact, if it's going to travel at the speed of light, it will take an infinite amount of energy to get it up to that speed, unless it has zero mass. So yes, we have to argue that it has zero mass. You can also see that from relativity. Remember, the difference between momentum in classical and relativity is a factor of gamma. Well, if V equals C in the gamma, you basically get a square root of 1 minus 1 in the denominator, and that goes to infinity. And the only way you can keep that from happening is if the mass goes to infinity at the same rate, because the mass would be on top. So that's another argument for the photon having zero mass. And then, of course, you look at this, you say, okay, well, I'm not sure the photon can even have kinetic energy now. Well, you can. Okay, in fact, that's all it has is kinetic energy and momentum. It has no mass energy. So if we use relativity, we know that E squared is equal to P squared C squared plus M squared C to the 4th. But taking M to be 0, we just get E squared is equal to P squared C squared. So we have another equation that you guys can make use of, and that's momentum P of the photon, which is given that symbol gamma, is just E over C. So if you take the kinetic energy, which is, like I said, the only type of energy it can't have rest energy. You take the potential energy, or excuse me, the kinetic energy of it and divide it by the speed of light, then you'll get the actual momentum. Any questions on that? Okay, so that's sort of the neat thing about this new photon. And we get the idea that these photons are coming in, and like when they are absorbed, if you will, what's really happening is they completely disappear. The photon disappears, and instantly the electron gets delivered some energy. And if that energy is high enough, then it will break off of the metal via the work function, because it's exceeded the work function. And the rest of that energy will go into the electron's kinetic energy. So we now have this concept, not only that light is a particle, but light is a particle that basically can disappear, as long as it's got sort of the right amount of energy, and that'll come into play a little bit later. All right. I don't know what that sheet of paper is. I don't know why it's there at all. Okay, that was weird. All right. So that was 1905. And things were still trying to progress. People were trying to make sense of it. By 1913, Bohr had been working in Rutherford's lab. So Bohr. I'm trying to not always write in cursive, especially with the names, because if you're not very good at reading cursive, or my cursive isn't very good, then it's better to be able to read. It's Ernst Rutherford. I think it literally does not have an E in there, but I could be mistaken. But Rutherford's a colorful character. He's the person that said, "Science is physics, the rest is stamp collecting." Which, like I said, I like to bring that up to my physics, to my friends in chemistry and biology and geology and all that good stuff. But I don't really feel that way. I just like acting like I do. So Rutherford is this guy who's trying to make sense of what nature has told us. So at this point, by 1910, 1911, 1912, Rutherford knows that electrons exist, and everybody else knows electrons exist, and they sort of pictured them as being part of the atom, and they thought the atom would actually have more structure to it. They thought you might be able to break up the atom, and obviously those electrons, which are such small things, were there. They also had discovered the alpha particle. So in fact, far as elementary particles goes, they believed that they had alpha particles, which turned out to be the helium nucleus. They did not know that at this time, but it turned out to be that. And then the second thing they found was the beta particle, which oddly enough was occasionally the electron, but sometimes it was the positron. It was a product of beta decay, hence they named it beta decay. And then they found the gamma particle, which turned out to be the photon. So that's sort of the particles they had. They didn't really have the neutron yet, and they didn't really have the proton yet. But Rutherford was trying to make sense of this. And in fact, they were working on something called the Plum pudding model of matter. So they imagined a blob of matter being like plum bread. Okay, in Great Britain, when they say pudding, that means bread, basically. So it's not literally a pudding, it's literally like a raisin bread or something. And what they imagined was that these little itty bitty electrons, which were, you know, multiple thousand times less massive than the alpha particle, is literally, this is 9.109 times 10 to the negative 31st kilograms, whereas the alpha particle is on the order of 10 to the negative 26th kilograms. So it's like a factor of 1,000, almost 10,000 times heavier. It's actually 2 protons and 2 neutrons, if that helps you. Okay, they didn't know that yet, but that's what it is. So they were working on that, and that just sort of saw matter as this blob, like a bread, and these little particles, which were thought to be elementary, the electron, were in there. Okay, maybe they had some of those gamma, some of those photons in there too. I don't know, but they were trying to map that out. So what Rutherford did is he took basically a alpha emitter. He took a gun that shot these huge particles, it's called alpha particles, at a gold foil. And why do you use gold? Because it's more expensive, and why shouldn't you spend all that money? No, there was actually a pretty good reason. They knew that one was pretty heavy, and they were more likely to actually be able to get some deflections to make sense of matter. So they were shooting it through this little foil like so. And since these alpha particles are so big, you expect them to come through and just barely be deflected at all, like maybe itty bitty angle here, itty bitty angle here, itty bitty angle here. Some of them won't be deflected at all, so on and so forth. But what turned out, and according to him, he was being a very thorough scientist, but according to some people that worked in the lab, no, they left one of the detectors back here behind the gun and it went off, and they're like, what the crap? So really what he discovered was that some of those things came back at him, and it was called Rutherford Backscattering. Okay, he said it was as if he shot a 16-inch cannon at a bowling ball and the cannon shell came back. So you can see that that's a really big deal, because he knew it was, you know, several thousand times heavier than the electron. How in the heck could that happen? Well, around that time was when Bohr was there, and Bohr was working with Rutherford, and I think he even worked under him. Might have got his PhD under him. I can't remember. It's been a while since I looked at that. But anyways, Bohr was there, and he knew that Rutherford had found something pretty important. And what Rutherford did was hypothesize the existence of a highly dense nucleus, because what he saw was the vast majority of these alpha particles went through undeflected. Like tons of them, like 95% of them went through undeflected at all. A small percent went and got deflected a little bit, but an even smaller percent got deflected completely backwards. So he reasoned that this thing must be super small. He suspected it might be 10 to the negative 15th meters. So he said, there's a nucleus. It would be 99.9% of the mass of the atom, and its radius is on the order of 10 to the negative 15th meters. Einstein's Brownian motion problem that he solved in 1905 had already shown us that the atom's radius was on the order of 10 to the negative 10th meters. So we're talking 10,000 to 100,000 times smaller than the nucleus. To give you some perspective, it's like we'd say if you raise the nucleus up to be as big as a grape seed, and we stuck it on the 50-yard line of the Washington football teams, who happens to finally be doing good because I'm not watching them, and you stuck it on the 50-yard line of their stadium, the electrons would be out beyond the parking lot. So the orbits would be bigger than the whole stadium, and including the parking lot. So that gives you some idea how big it is. So that became a model, and in fact, it became the nuclear model or the planetary model. They pictured a nucleus with the electrons orbiting around here, here, maybe even like this, so on and so forth. And that was the model of the atom. The problem with that is electricity and magnetism that Maxwell had given us showed us then when charged particles like the electron change direction or speed up or slow down, that causes radiation. And you don't just get energy for nothing. So you'd actually expect the electrons to slow down and ultimately run into the nucleus. Oops, put the thing in the wrong order. So that's what you'd expect. So it actually predicted the short lifetime of atoms, and we knew that wasn't the case, right? Lifetime, the atoms seem to last pretty long and be pretty stable. But according to Maxwell's equations, you're actually not going to be able to do that. Those things are going to deflect, are going to lose energy over time. So Bohr went to try to figure something out with that. And by 1913, 1914, I think it was, he actually came up with his Bohr model of the atom. And he did so by using and thinking that this quantum mechanics that crazy Einstein's been running with must be of some use. And he tried, quantizing the energy, saying energy is equal to some n times something. And he couldn't get this equation that we already knew from some other experiments. So he comes up again with the same sort of model that Rutherford's talking about, but he's trying to make sense of another experiment. And that experiment is called, or that result is basically called the spectra of matter. So it turns out if you take a evacuated glass test tube, say, so let's imagine you have a glass test tube, looks like a neon light. In fact, the neon light is exactly what I'm talking about, okay? Well, they knew at this time that you could take a glass test tube like that and you could heat it up and stick a little wire probe in one side with maybe a little metal disc, and then the same thing on the other side with a little metal disc, and even be a long distance like this, say, and then they could connect to a valve on that test tube and suck all the air out and then quickly backfill it with a pure element. So you suck all the air out, and then before you close off, you connect it up with, say, hydrogen gas or helium gas or mercury vapor or water vapor or oxygen gas or nitrogen gas. And you fill that back in and then you close off the thing, and it's almost a vacuum, but it's got a low pressure with some gas in it. And that gas is mostly pure. They knew that when you apply a huge amount of voltage to this, I'm talking 500 to a couple thousand volts across that, and your book has pictures of these in your as well, so you can see one. When that happens, you get sort of that neon light effect. You'll see literally a stream going right down the axis of that test tube, glowing in some color. Like when you look at it for hydrogen, it looks sort of red. It looks even more red when you look at it for neon. If you look at it for mercury, it looks a little blue. And probably you've seen street lights that look kind of blue. Have you ever seen street lights or parking lot lights that look sort of bluish? Those are actually what my dad used to tell me were mercury vapor lights, and he could tell it because the mercury color. Mercury, in fact, does look blue when you do that with a test tube. And the ones you normally see more of are sort of a yellowish hue. Have you seen parking lot lights that are yellowish but not LED? Those yellows, yeah, those are sodium vapor. My dad worked for Dominion Power, so he worked on those things. He retired from there. So those are sodium vapor lights, and you're actually seeing again that kind of light that we're talking about. Now here's the cool thing: if you take that light and you try to shape it to where you only get a little bit amount by maybe running it through a thin slit, just one, okay, and then you run that light, or you could do a hole if you wanted to, but the thin slit works really well. And then you run it through a prism. What will happen is you'll see that light is actually a mixture of a few colors. In the case of hydrogen, you only see like 3 or 4. And it's like you'll see a really bright line that's sort of a bluish. You'll see a really bright line that's sort of a reddish. You'll see another reddish and then an orangish light, and that's about it. But when you do that with a different gas like helium, you'll see like 12 lines. And then when you do it with a different gas like oxygen, you'll see 30 some lines, and nitrogen more lines. And if you do something like water vapor, you get a ton of lines because that's actually a molecule. Well, they knew that, and they knew that could be really awesome for chemists because chemists could easily figure out what a substance is by heating it enough to become a gas, putting it in one of those tubes, and then looking at the wavelengths of the light to come out of it by using a spectrometer. And that's how we get these spectrometers now. There's various types, by the way, but one of them that we're talking about looks like a telescope, and you literally just align it, say, with a hydrogen gas tube. You get the angles figured out to a relationship with wavelength, and then you put an unknown gas in there, and that can tell you, now that you've got it calibrated for hydrogen, that can make a formula that gives you exactly the wavelength for other colors. And for other gases. So then you get the wavelengths for the other gases, and then you can go in a book of chemistry and it'll have the spectra for that material. And if you find one that has those particular wavelengths, then you found that element. So that was a really powerful thing. But it was well known that nobody knew why the crap it was doing that, right? In fact, you often hear the story that some middle school math teacher had even contrived a formula for it, and his name was Balmer. And we have now the Balmer series, which is the series from the hydrogen atom that makes the visible spectrum. It has some in the non-visible as well, but the visible part of the hydrogen spectrum is in the Balmer series. And he created a formula that actually worked, but it had no meaning. It just had a constant in it and had a 1/1 squared minus 1/n squared in it, and that would give you the 1 over the wavelengths. So Bohr said, I would like to try to match that equation. So Bohr takes that conservation of angular momentum thing. I'm going to go back to my page now. So Bohr takes this linear angular momentum thing, and he says, let's pretend for a second that it's n times h. That didn't work out. He got a crappy formula. But then he realized, wait a second, if I put 2 pi in there, then he gets exactly the right formula. So he's basically, for no reason other than it gave me the right answer, he says, I'm going to assume that angular momentum, which for a point particle is the mass times the velocity of the particle times the distance it is away from the center of rotation. He said that's going to be some integer n times h over 2 pi. And we now call that quantity h bar. And it's 1.055 times 10 to the negative 34th. So you see it's now an important value that comes up. But actually the 0 doesn't even matter. So it's really 1, 2, 3, so on and so forth, right? So when he did that, that would give him something that relates an integer n to the velocity that the thing would have. And then you just say, well, wait a second, mv squared over r has got to equal, from your class, it was e squared, because the electron and the proton both have the same charge E, and we never really take into account the signs. Remember how we did that in Coulomb's law? Over 4 pi epsilon naught r squared. So you set that equal, you have a stable orbit, but you now have an extra relationship for how m times v times r is supposed to behave. And lo and behold, you get this formula. Okay. This, by the way, is Z. And that's for the general case. Like he imagined a scenario in which you could have any number of protons in the middle or any number of nucleons in the middle of charge E, right? Now, he got this formula, which is exactly the same. Like if you compute this number, this is exactly the constant that Balmer guy, who was actually a math teacher at a girls' school. He wasn't actually a middle school. It was an all-girls school. He had his PhD in math, and he was actually a very brilliant mathematician. But by doing that, Bohr was able to derive this very expression, and it gave it to him in a more general format, because the Balmer series had only this being 1. But it turned out later that there was a Lyman series and a Paskin series, and the Lyman series was, I think the Balmer series was 2, the Lyman series was 1, and the Paskin series was 3. Y'all need to look that up. So Balmer, Lyman, and Paskin. Okay, so you should know what they correspond to for each of those. Like that. Okay, that's, in other words, that's the kind of question that you'll see worked in the book as well as worked in your homework as well as possibly in your final exam. So that's a pretty straightforward formula. What it basically says, and this is the big deal now, what Bohr has found is there's certain allowed orbits. So you see the nucleus right here. And you can't have an orbit just anywhere. You have to have an orbit at a very specific spot. And this is where n equals 1. And then there's another one for n equals 2. And in fact, they get closer and closer together the farther you go out. And that turns out to become the principal quantum number later. But it starts off with this, and this turns out ultimately to be completely wrong. But it's sort of like God left us a little stepping stool in front of the sink of the kitchen, so that we can just look over the edge and get some idea about what's going to happen, right? It gave us enough of an idea to think, oh, waves. Let's think about waves. Let's think about waves. Okay, and then you think, okay, let's make a wave equation, and then next thing you know, Schrodinger makes a wave equation, and darn, it works, right? So when he did this, what he discovered was that these two ends have very specific meanings. If you take the energy of n prime and the energy of n, in other words, maybe n prime is 2 and n is 3. So this could be n prime and this one could be n, for instance. When you do the subtraction of those two and you set that equal to, so let's say En minus En prime equals hc over lambda. Remember, that's the form that we found for energy a second ago using HF and using the fact that C equals F times lambda. When you do all that, you end up getting an expression that has 1 over n squared, n prime squared minus 1 over n squared. So if an electron were to go from here to here, then it goes from a high energy state to a low energy state. So it has to, you can't just violate conservation of energy. So it creates a photon. And that photon has a wavelength given by exactly this. And since it's exactly that, that's why you only get very pristine, narrow lines in the spectrum, say, of hydrogen. One of them corresponds to falling from n equal 3 to n equal 2. Another one corresponds to falling from n equal 4 to n equal 2. Another one corresponds to falling from n equal 5 to n equal 2. Those are the Balmer series, if I remember correctly again, but I'm advising you to double check that. I think the Balmer series is the one that falls to 2. Actually, I can look that up real quick, just in a second. Yeah, the Balmer series was n equal 2. So Balmer is n prime equals 2. And later they found that the Lyman series was n equal 1. And the Paschen series was n prime equal 3. So now I've written that for you on your notes, and all this will be available at least within an hour and a half after class. Okay, so what's going on in the Balmer series is various electrons are falling from higher levels to n equal 2. In the Lyman series, they're falling from higher levels to n equal 1. In the Paschen series, they're falling from higher levels to n equal 3. And of course, all of those are possible. But what you see is there's only a certain amount of energy that can be accepted by an atom. So if some photon comes flying by an atom, the atom sort of looks at the photon and says, hey, I know that energy. You're hc over lambda, and that happens to be the energy that is the difference between n equal 3 and n equal 4. So spontaneously, the photon will disappear, and also spontaneously, the electron will jump up to making the atom in an excited state. So if the photon has the exact same energy as the difference between this energy level and this energy level, then the photon will be absorbed and you get what's called an absorption spectrum. And that one's more or less a whole rainbow with missing spots. With missing lines. Now, the red one, on the other hand, that's called an emission spectrum. Spectrum is a singular and spectra is the plural, by the way. And that's just few bright lines. Now, if you get into molecules, though, you can have millions of lines, but still, it's not a whole rainbow. It's just a bunch of parts of the rainbow. And in fact, if you have the emission spectra from hydrogen and the absorption spectrum from hydrogen, and you put them on top of each other, they'll make the whole rainbow. But that's true for any element. If you did it for oxygen, the emission spectra on top of the absorption spectra would fill in and make the whole rainbow. So that's ultimately how we now in astronomy can look at a star, use a spectrometer on that star, break its light up into various wavelengths, and we can tell exactly what it's made of, not only by what elements and compounds are in there, but by how much percentage, because the brightnesses of the lines and how they compare to other lines allows you to work all that out. So that was the Bohr model of the atom. That was the thing that made us think, okay, there's quantized levels that the electrons can be in and they can't be in other ones. It turns out, of course, the electrons aren't following orbits like that. They're actually, there's a probability density that exists that we learn about from quantum mechanics. And it turns out that the average distance was exactly the same as what Bohr's model came up with. When he tried to apply this to any atom with more than one electron, it failed. But he could do like he could do helium with only one electron and it would work. But if he did helium with two electrons, it failed. So this model was, like I say, it's just a little hint, like, hey, let's let you look at this and maybe you can get the start. So it's really kind of neat how, you know, nature sort of leaves these things behind. Now that was 1913, 1914, something like that. And he really had no idea what's going on. But around that time, Louis de Broglie, so here's that name, Louis de Broglie or Louis de Broglie, not really sure. He was actually trying to make sense of why Bohr's model of the atom worked. And he also did not like the fact that there was this fundamental asymmetry in nature. We had, for instance, matter, which we've always thought of as particles, and we had this thing of light, which we always thought of as waves. Now, all of a sudden, light can be viewed as waves like it always was, but it's also particles. Well, matter is always thought of as particles, and he couldn't imagine a universe in which this would exist in two different ways, but this wouldn't. So Lewis hypothesized that lambda is equal to h over p. And not only was he right, he's right in the sense that it also works for classical physics and for relativity. So if you put P equals mv in there, you get the right answer for things that aren't going, you know, within 1 or 2 or 10% of the speed of light, and it works fine. But you can also put gamma mv in there, and you get the right answer. So he predicted the existence of a wavelength for matter. And in fact, you can calculate, as your book does, the wavelength of electron given a certain kinetic energy. And again, those are really simple examples. You're just literally calculating the mass times velocity for classical, or you're calculating gamma times the mass times velocity for a given particle, and that gives you the wavelength. And it turns out that typically the energies, low energy electrons, have about the right wavelength to probe the atom or the molecular structure or the atomic structure of materials. So basically the spacing between atoms is comparable to the wavelength of the electron. So de Broglie did that. And what that allowed him to do was also say, wait a second, for n equals 1, it turns out that 2 pi times the radius for the first orbit of Bohr, n equal 1, is actually equal to 1 times the wavelength of the electron. And for n equal 2, he found that 2 pi times R2 was equal to 2 times the wavelength of the electron in state 2. So all of a sudden we had some sense made of Bohr's model. The first orbit on average is that, but in reality what it means is it goes half a wavelength and then the other half of a wavelength. So this is the positive hump. This is the negative hump. If you draw the second one, though, it makes a little bit more sense. Actually, I'll draw the third one because that one's kind of cooler. I'm going to leave this one right here. The third one actually has 3 wavelengths in it. So you can go like this. Oops. Went too far there. Like that. So the distance around is 1, 2, 3 wavelengths. So all of a sudden, thanks to de Broglie, and he won a Nobel Prize for it, by the way, thanks to de Broglie, we had an understanding of why it was the way it was. Okay, and that's basically all of chapter 37. Okay. Now in chapter 38, we introduce Schrodinger and Heisenberg, and this is a crazy thing. So Schrodinger and Heisenberg are working on the same science as everybody else, but they all go back to Bohr. Bohr is sort of the big brain in the room, as is Enrico Fermi, who's not quite come into his own yet, but he is definitely a brilliant person, probably one of the most brilliant people we had helping us during the Manhattan Project. He was many people that worked there. So the reason we got a nuclear weapon in the time we did was because of Enrico Fermi. That's why they have a Fermi lab at University of Chicago and all that good stuff. But basically all those people were coming together, but Bohr was sort of leading the way. People were confused. What the heck is light? Well, it's got this principle of complementarity that Bohr suggested, and that's spelled COMPLEMENTARITY. So it's double E's, not complement with an I in it. Okay. That is like Jerry Maguire's you complete me. That's what that one means. So you can't say light is a wave. You can't say what light is a particle. What you can say is light is a logical construct that sometimes acts like a wave and sometimes acts like a particle. And you don't know what it's going to do until you do the experiment. Okay. The good news is once you do the experiment, every time you do it, it'll behave exactly the same way. It doesn't flip-flop or anything like that. So that was sort of a guiding principle, is that these matter waves actually have both parts that have to be taken into consideration. And he also introduced an idea of a principle of the correspondence principle. Okay. And what that means is, hey, we've got Newton's laws of physics. They work really great. We got Newton's law of gravity. That works really great. If we have a realm where Newton's laws has given us a good equation, then this new theory that we're working on, this new hypothesis, this quantum hypothesis that we're working on must give us that same answer because it worked so well before. And that was actually a bigger part of it than most people understand, because there's Poisson brackets, which is not unlike the brackets that we use in quantum mechanics and in the more advanced graduate courses. And that would allow them to do little manipulative stuff to help form the equations. But at the end of the day, what they decided was we need a wave. And you guys in chapters 14 and 15 studied waves. And one of the equations that you might have used was, for instance, the wave, which, by the way, we use the Greek symbol psi. So I'm going to write that down and show it to you. We use the Greek symbol psi to represent the solution to the Schrodinger equation. And it's weird because the Schrodinger equation actually has an I in it, square root of -1. So this thing has a I in it potentially, and therefore is meaningless to us, right? It can't mean something because it's a fake number, basically, an imaginary number. That was the word I was going for. So this psi, you know, from your wave equations of chapters 14 and 15, you know that one way you could say that would be A times e to the I, and then you say kx minus omega t. That's the equation for a wave. What we normally did was we did A cosine kx minus omega t, and that was a wave traveling to the right. And we also learned that A cosine kx plus omega t was traveling to the left. Okay. Well, one way you can think that Schrodinger might have came up with a wave equation is he knew that the wave equation has the form, the second derivative of some displacement with respect to position squared is equal to 1 over the velocity squared times the second derivative of that displacement with respect to time squared. That's the fundamental form of a wave equation. And you can also realize that K is equal to 2 pi over lambda. And since we have E equals HF, we can say since omega is equal to 2 pi times F, then we can multiply both sides by 2 pi and we get 2 pi E is equal to H times 2 pi F. Well, this is just omega. And that gives us that E is equal to H bar over omega. Okay. So you could actually rewrite this equation as hk, because if you multiply h times k, you get h times 2 pi over lambda. But if you change that to h bar times k, then you get h over 2 pi times 2 pi over lambda. So what actually happens there is you just get h over lambda. But this is exactly k, and this is exactly h bar that I warned you about. So what we can do is, instead of writing psi equal to a times e to the I, we can write a times e to the I h bar times, in this case, we're going to say k minus 1 over omega, or excuse me, yeah. Oh, excuse me, 1 over e times t. Okay, so you can sort of get it out that way. That sort of gives you a nice expression. So this is a way you could do it, but you think, well, there's got to be derivatives. So what is the first derivative of psi with respect to x? Well, if I look at this form, we could also do it with that form. Oh, that's what I forgot, kx, stupid me. Okay, if I did it with this form, I can see that the first derivative is going to be I times k times e to the I kx minus omega t. And then I'd say the second derivative of psi with respect to x squared would be I times k squared times e to the I kx minus omega t. Well, that's just negative k squared. So we get second partial psi with respect to x squared is equal to negative k, remembers 2 pi over lambda, but we're just going to write it as k squared right now. So negative k squared e to the I kx minus omega t. Now, if you take the derivative of psi, or excuse me, the first derivative of psi with respect to t, we get, in this case, negative I omega times e to the I kx minus omega t. So that's our expression. Now remember this, we know that P is equal to h over lambda. So classically, we know that kinetic energy is equal to P squared over 2m. So that's actually equal to, putting in what we know, for instance, h bar k. You see that that's h over lambda. So h bar k is actually equal to the momentum. So I can say k is equal to h bar squared k squared over 2m. Now that k, of course, is 2 pi over lambda. So you can see it could relate to lambda like that as well. And you could also see that, let's say the energy is equal to h bar omega. That's another expression we were able to find. And we have negative I omega. So if I took and multiplied, let's say I multiply the second derivative of psi with respect to x squared by negative h bar squared over 2m, what do I get? I get negative h bar squared over 2m times negative k squared e to the, or excuse me, yeah, negative k squared e to the I kx minus omega t. So I think you can see that this becomes, did I get that right? Wait a second. Oh, this was squared too. So this was just -1. Sorry about that. Remember, this turned out to be just negative k squared. So I put that in here. So now I can see that this is h bar squared k squared over 2m times psi. So Schrodinger might argue, well, this is clearly the kinetic energy. So he's realizing that this is like an operator. Operating on psi. So negative h bar squared over 2m second partial with respect to x squared actually in 3 dimensions becomes negative h bar squared over 2m del squared. That's an operator. That's kinetic energy. Okay. So what he wants is a conservation of energy equation that says kinetic energy plus potential energy is equal to the total energy. So he looks right here, and I've already got the omega here. So if I take partial of psi, or excuse me, the first partial of psi with respect to time, if I take that and multiply it by negative I h bar, then look what happens. I get, according to this, partial of psi with respect to t is negative I omega. So I already have a negative I h bar right here from that thing. Now I'm going to multiply that by negative I omega e to the I kx minus omega t, like that. And what do I get? I get, in fact, positive h bar omega e to the negative I, or excuse me, that was positive I. I don't know why I have a negative there. Times kx minus omega t. So this is, in fact, E psi. So it looks like conservation of energy could just be negative h bar squared over 2m d2 psi over dx squared plus the potential energy, which you might call V, times psi. And that's going to give me equal to what I had to multiply by, which is negative I h bar partial of psi with respect to t. And that is a wave equation. It doesn't necessarily look like it because this is only first order in time, but the fact that you have an I here means you have 2 components, so you can still make a wave equation out of it. By the way, you can also get rid of that negative and call it I over h bar. So you could also say I over h, or excuse me, h bar over I. Said that backwards. You can say h bar over I partial of psi with respect to t. That is actually Schrodinger's equation. In one dimension, you just use a regular derivative. In one dimension, where you're treating the energy as a constant, there's another form. You could say negative h bar squared d2 psi over dx squared plus, maybe you don't like V, you might want to use U, that's acceptable as well. Psi is equal to E psi. That's called the stationary Schrodinger's equation when the energy is fixed. And then you have, of course, if you want to do full force ugliness, it's negative h bar squared over 2m del squared psi plus U psi is equal to h bar over I partial of psi with respect to t. Okay, so this one's when psi doesn't have any t dependence. It's called a stationary state. So Schrodinger came up with this equation, and it works, but as you can tell, it was made up of, p squared over 2m, which is classical. So immediately Dirac realized it was wrong and immediately tried to correct it by making the Dirac equation, and he actually did get it, and that led to him predicting the existence of antimatter and all that good stuff, because people said his equation must be wrong because it gave him negative energies, and he said, au contraire, my equation's right, there's going to be antimatter, and lo and behold, shortly thereafter we found antimatter. So that's the Schrodinger's equation. And the big thing about Schrodinger's equation is you can tell the psi comes out to be possibly something with an I in it. So how could that possibly be anything meaningful? Well, it can, and it turns out that if you take psi and you take its complex conjugate, which remember, if z is equal to x plus I y, then z star is equal to x minus I y. So you just change the sign of the I in there. If you do that and then take psi itself, multiply it, you get something called psi squared, which is the probability density. So if you're doing psi for a bunch of particles, it's the probability that the once you multiply it by dV, some volume element, this quantity right here is the probability of finding the particles in dV. I don't know why I wrote uppercase D, but inside the volume element dV. If it's for one particle, then it gives you the probability of that one particle being at a particular point in space. Okay. Or if you do that, then you can find the probability of it being over a certain range of space by integrating this from, x equals 5 meters to x equals 6 meters. That would tell you the probability of it landing in between x equals 6 and 7 meters. So the typical problems that you solve are ones where that potential energy function is a constant. So like if you took, for instance, a system like this where you had a well that's infinitely deep, so that goes to infinity, that goes to infinity, and maybe this is your y-axis and this is your x-axis. The fact that the potential is infinity out here means there's no wave function. So psi equals 0 and psi equals 0. And then the wave function has to be continuous. So psi has to be equal to 0 there, and it has to be equal to 0 there. And if you use psi equals, let's say, a times the sine of kx, because this isn't one that depends on t, you usually use a lowercase psi for that, then you can put that in there and you'll get, or kx plus phi, I should say. And you can put that in the equation, apply these boundary conditions, and you'll get the fact that it should look like this for n equal 1. It'll look like this for n equal 2. It'll look like this for n equal 3, so on and so forth. And your book does these problems, and they're pretty tricky, yeah, but they're not they're the thing I would love you to be able to do, but you're not required to do. Okay, you are required to be able to apply the results that come from them. So I've given you enough of the background information, and I'll follow up a little bit more with this. But notice on my YouTube channel, I do have some a problem worked out like this, and a derivation of Schrodinger's equation that way. At the same time, we also had Heisenberg came up with an alternative form that was nothing but matrices, but it turned out to be exactly the same. And his gave us this idea that delta x times delta p sub x is greater than or on the order of h bar, which is h over 2 pi. And also the delta E times delta T is on the order of or greater than h bar. That's the uncertainty principle. And your book talks about that. And I've talked about that already when we talked about in the 241 class when we talked about elementary particles. So we've done essentially all of 37 and 38 now, skimming it as I was, but hopefully I explained the concepts well enough where you can make sense of the problems. The problems are way harder than the problems I'm going to give you on the test or than the problems I'm going to give you on the final exam. So try that quiz that I left for you. Obviously time's up, so you guys are free to go. But thanks for coming, everyone. I'll have these notes posted within an hour and a half, probably.
Just a quick question on the review. On the review for Thursday. Should we email you questions beforehand, or just have our questions ready on that day?
If you have your questions ready on that day, that'll be fine. If you send them to me early, I can make sure I know how to answer it. That would help me a little bit. It might help y'all, because if I get, you know, screwed up in the middle, then y'all wouldn't have to deal with it. So either way you do it's fine. I'm supposed to be good enough to figure it out on the fly, but there are times when you make a careless mistake or something that ruins everything. I think someone else is going to ask a question when Clarence was asking his. Anybody?
I wasn't the person talking earlier, but I had a question as well. What is the best way to contact you? Like if we have any questions or anything, let's say between like Thursday and Tuesday?
Yeah, the text messages are the best way. That's why I gave everybody my phone number. I'm not going to say it out loud because I'm still being recorded.